Hello everyone, welcome to Physics Rocks It's True. This episode is about kinetic energy. We're going to look at where the equation for kinetic energy comes from, how it's related to work done, and then we're going to take a look at some examples of how it's used and some of the implications to the formula that it creates. So let's get started. Alright, so in this situation, let's imagine that we have a catapult as designed by some rambunctious young child that has put some elastic strain energy in and is going to fire a projectile of some description with kinetic energy. Now, let's make the massive assumption that this is 100% efficient just to keep life nice and simple for us. Then what we would have is that the elastic strain energy going in, let's say that's 50 joules, is going to be equal to the kinetic energy coming out, which is 50 joules. It would therefore be reasonable for us to say that the work done is equal to 50 joules. Okay, because remember, work done is the energy transferred from one form into another. In this case, we've got it only going from one form into one other form, so we've done 50 joules of work. Now that's kind of cool because we can then do the equation that work done equals force multiplied by distance. Okay, so we know that 50 joules is equal to the force multiplied by the distance moved. But that's not massively useful. If I'm firing a catapult at something, all I really want to know is how fast does it go. If I increase the energy, I don't want to know how much more force I get. I don't want to know how much more distance. Well, I might want to know how much more distance I get, but I definitely want to know, does it get faster? And we can use this idea of work done equals force times distance and one of Newton's laws of motion, that is v squared equals u squared plus 2a in our other bit here, which is v squared over (2d). And then we're going to multiply that by d because we have to at the end. So what I've done in the red is I've just replaced a with this. Alright, now what happens here is that we've got a divided by d and a multiplied by d. They cancel each other out, and that gives me that ek is equal to mv squared over 2. Because the 2 got left behind, the d got cancelled out, but the 2 did not. So mv squared over 2. This is the equation for kinetic energy. It's much more commonly written though as ek equals a half, which takes a bit of drawing on this. So 1 over 2. So a half mv squared. Okay, you will never ever be asked to derive this equation, but I don't like just presenting you with stuff as if it's some form of inalienable fact that you just have to accept. This is where it comes from. Okay, so if I highlight that, this is what you need to know. Kinetic energy, Ek, is equal to a half mv squared. That means that the kinetic energy of any object at any given time is equal to a half multiplied by its mass multiplied by its velocity squared. Alright, so some points to note about this. Kinetic energy, just like work done, is going to be measured in joules because it's an energy. So that gets a symbol J. And because we've restricted ourselves to energy in joules, we must now use standard units. So mass here has to be in kilograms. And the velocity here, or the speed, has to be measured in meters per second. So this is speed in meters per second. Once we've got that, we can now play with this a little bit. Okay, so let's set ourselves up a little situation. Let's imagine that an object travels at 5 meters per second and has a mass of 10 kilograms. Right, so let's see what we might want to know. We might want to know A, how much kinetic energy it has. We might want to know how much work had to be done to make it move this way. And we might want to know if it took, say, 4 meters to make it get to 5 meters per second, what was the average force acting on it? Okay, so this basically takes in everything that you need to know and everything that you can play with in kinetic energy. Right, so this is what it's about. Now, in reality, the big use of kinetic energy is the fact that, yes, you can work out the work done on something, but the truth of the matter is, if you see a car driving down a street, you don't know how far it took to accelerate. You don't know how much force the engine was producing. So therefore, you can't actually work out the work done to get it to that speed. But the likelihood is that you probably can go and look up some specifications and figure out roughly what its mass is. That you can go and get a radar gun and work out how fast it's going. Or you can even just work out how quickly it's progressing between lampposts or anything with a known distance and time. So finding out the speed of an object and the mass of an object tends to be significantly easier than finding out the force that was acting on it in the past and how far that force acted on it. Okay, so this is what we want to do. So how much kinetic energy does it have? Straight up, dead simple, let's look at what we've got in our equation. We know that the velocity or the speed is 5 and it's in the right unit. We know that its mass is 10 and is in the right units in kilograms. And we want to know the kinetic energy, EK, equals question mark. Okay, so we just whack on with our equation. EK equals a half mv squared. So EK equals, instead of a half, we'll write 0.5, just keep it mathematically neat, multiplied by the mass, which is 10, multiplied by 5 squared. Now notice it's just the 5 that gets squared here. It's not the whole thing, it's just the speed that gets squared. We go and grab our calculators on that one, and we pop it all in, and we get that the kinetic energy, EK, is equal to 125 joules. Alright, simple as that. Now, how much work had to be done to make it move this way? Now, this is a straightforward 1 mark question, but you need to understand what's happening here. If this is our object, what's usefully coming out of this object is 125 joules. And that's of kinetic energy. So some amount of energy had to go into this object. And at a minimum, that had to be 125 joules as well. 125 joules of something. Now, we're not told about it having any wastage. We're not told about it being inefficient or anything along those lines. So it's okay for us to assume that it's perfectly efficient. So what happened? 125 joules got changed from one form into another. That is the definition of work. Work done is equal to energy transferred. So therefore, 125 joules got transferred, so therefore the work done is just 125 joules. Alright, I'm going to just grab all this and shrink it so that we can keep part C on the screen whilst we work with it. So that just pops over there. So if it took 4 meters to make it get to 5 meters per second, what was the average force acting on it? Right, well, let's have a look at what we've been given here now. It took 4 meters, so we've got a distance equal to 4. We've got a force that we want to find out, and we've just been asked what's the kinetic energy. That's 125, and what is the work done? That's 125, and we also know that the velocity is 5, and we know that the mass is 10. So we've got a lot of information here, so we need to pick the right one. Now, we only have one energy equation that has force in it, and that is that work done equals force times distance moved. And that makes sense in the context of our question because we've been given the distance in this part. So that's what we're after here. The work done is 125. The force is what we want to find out, and we know that the distance is 4. So we substitute in our numbers. We go and grab our calculators again so that we can divide both sides here by 4 because we don't want F times 4. We just want F, And that allows me to go and calculate that 31.25 equals F. Written more nicely then, F equals 31.25 newtons. And it's as simple as that. And it works the other way round. If I know that something has 5,000 joules of kinetic energy, I know that 5,000 joules of work need to be done to stop the object. And this allows us to work out how much force is required to stop a moving object. Now, if you consider things like braking distances and stopping distances in cars, this is critical. If you know that a car is traveling at 60 miles an hour, you roughly know what the human kind of reaction time is, then you can build in to your car what the stopping distance is. And if it's not short enough, if it's not short enough to be safe, then you need to build better brakes. You need to build something that can actually apply more force. Because in the situation where something's braking or slowing down, what you have is this situation, that you have a car or a lorry or anything that needs to be slowed down. Going into this situation, we have, let's say, 5,000 joules, and we've got 5,000 joules of kinetic energy. And at the end of that process, we want 0 joules of kinetic energy. This is one of the very few situations where we want to waste everything. Okay, we need to waste 5,000 joules of energy, and we need to waste it pretty sharply if we want to stop in time. So we want 5,000 joules of heat and sound. Actually, you slam on the brakes. How much work's done here? Well, 5,000 joules of energy gets turned from one form into another, so the work done is equal to 5,000 joules. And if I happen to know how far it takes to do that, or I happen to know what the braking force of the car is, let's say we've got an engine braking force of, I don't know, 2,000 newtons. Right, completely pulling that out of the air. Right, so if I'm doing 5,000 joules of work, I've got a force of 2,000 newtons to do that. I want to know how far that's going to take me. Then I have work done equals force times distance. So 5,000 equals 2,000 times the distance, divide both sides by 2, and that gives me divide both sides by 2,000, that gives me 2.5 equals the distance, so the distance is 2.5 meters needed to stop this thing. Okay, so it's not going to stop instantly, it's going to stop in a certain distance time. And that's kind of handy. Now, last thing then, why do sports cars cost so much? Because at the base of it, you know, a good car, let's say a really good car will get you from 0 to say 60 miles per hour in around about 4 seconds. I mean, that's a good car. Let's work on that. The kind of bottom of the range car type of thing that, you know, teachers end up driving, get you 0 to 60 in about 25 seconds. But the difference in price here is not a factor of 6. It's a factor of much more than that. And that's because of the kinetic energy problem. Okay, so let's take a look at this. Let's imagine that I have something of mass, let's give you 1,500 kilograms, okay, a reasonably smallish car, a smallish car anyway. Mass of 1,500 kilograms. And we needed to get to a velocity equal to 28 meters a second. So somewhere in the region of 60-ish miles an hour. And I need to know how much work that's going to take to do it. Now, if both of these cars are able to do that, let's see what we've got. We've got EK equals a half mv squared. Okay, so our really good car, not the 60, is going to reach this in 4 seconds. So the kinetic energy available is equal to 0.5 multiplied by 1,500 multiplied by 28 squared. So once again, we go and grab our calculators. We do 0.5 times 1,500 multiplied by 28 squared. And that gives me 588,000 joules of energy to get me from 0 to 60 in 4 seconds. All right, now let's take a look at our little crappy car. Our little crappy car is not going to get from 0 to 60 in 25 seconds. But let's give it its dues. Let's imagine that it gets from 0 to 30 in 4 seconds. All right, that should take half the energy, right? It's doing half the work. Okay, it's getting to half the speed in the same time. You'd think that, wouldn't you? All right, so half the speed. So let's get V equals 14 meters per second in this case. That's not quite 30, but it's good enough. So for our little dodgy car, which is still doing pretty well at 4 seconds, EK equals 0.5 multiplied by, same equation as before, 1,500, we're assuming it's got the same mass, times 14 squared. Go and grab your calculator on that one, and that gives me 0.5 multiplied by 1,500 multiplied by 14 squared. And that gets me an answer of 147,000 joules. And that's not half. Okay, the eagle-eyed amongst you will actually notice that it's a quarter. So even though it's getting to half the speed, it's taking a quarter of the energy to do it. So in 4 seconds, an impressive car needs to put out 588,000 joules of energy. In the same 4 seconds, a lesser car, to get to half the speed, needs to put out a quarter of that energy. And that's why, to get this number down and down and down and down and down, in order to half the time it takes to get to a speed, what you need to do is you need to quadruple its ability to deliver that speed or deliver that energy. And that's an issue. That's an issue. And it's because of this. It's because the velocity is squared. Right? The kinetic energy required to get to a speed, EK, the work you need to do, is proportional to the velocity squared. And what this means is that if you want to double the velocity, you need to multiply the kinetic energy by a factor of 4. If you want to triple the velocity, so you want to times that by 3, you need to multiply the kinetic energy by a factor of 9. If you want to quadruple your velocity, you need to multiply your kinetic energy by a factor of 16. It's a squared relationship. So doubling one doesn't double the other. Doubling one double squared is the other one. Okay, so that's 2 squared, which is 4. If you want to triple it, it's 3 squared, which is 9 times the energy. Quadruple it, 4 squared, 16 times the energy. And that's a big deal. That's a big deal. All right, folks, I've taken quite a bit of your time on this one. What I want you to do now is go to the link in the description below, grab the little worksheet on that, and then I want to try the questions there. Come back and see me in a couple of seconds' time, and we'll go through the answers. See you shortly. Okay, everyone, welcome back. Let's have a crack at these questions. So first up, nice and simple, state the equation for kinetic energy, define any terms, and identify the units that they should be measured in. So straight up then, you get EK, kinetic energy, equals a half mv squared. Now we need to define any terms that we've used. So we've used 3 terms here. We've used EK, m, and v, and they are EK is kinetic energy. Pop that over there. M is mass, and v is velocity. And then we need to say what are they measured in. So kinetic energy is measured in joules, or just J would be fine. Mass is measured in kilograms, kg. We'll try and line that up a bit better. And velocity is measured in meters per second. And m/s would be more than fine for that. Okay, so there's 3 marks for this question. Where are those marks? You get 1 mark for getting the equation correct, then 1 mark for getting all of your terms correct, and then 1 mark for correctly identifying each of the units. Simple 3 marks for you. On we go then. An object is travelling at 7 meters per second and has a mass of 14 kilograms. What is the kinetic energy? Now, good idea here, even if it's a simple question, is still to list what we've got. So it's travelling at 7 meters per second, so we know that that's a speed and it's in the right unit, meters per second. We know that the mass is 14 kilograms and we're being asked to find the kinetic energy. So again, we just pop it into our equation that EK equals a half mv squared. So EK equals 0.5 multiplied by 14 multiplied by 7 squared. Now you can probably do that in your head, but I strongly recommend against it in an exam situation, because in an exam your brain tends to play tricks on you and you get stressed. So get it into your calculator and get 343 joules. Job's good. 3 marks, formula, working and answer. So formula, working, answer. This bit over here is technically worth 0 marks, but in an exam situation this will help jog your memory as to which equation it is you want. Question 3, an explainy one, everybody's favourite. Explain why doubling the speed of an object is not simply a matter of doubling the work done and accelerating from rest. Assume 100% efficiency. And there are a couple of marks available for this one. Okay, so what we're looking to say here is that if you quote the equation that EK equals a half mv squared, then you can say that kinetic energy is proportional, or directly proportional even. You could say depends on, though, like you can probably get away with that, but kinetic energy is directly proportional to velocity squared. And then you need to go on and explain that. Therefore, doubling the velocity requires multiplying by 4 the kinetic energy. And that's you, okay? So 2 marks here. 1 mark for in some way suggesting the kinetic energy is dependent on velocity squared, and then 1 mark for explaining what that means, that in order to get this doubled, you now need 4 times the kinetic energy. So you get 2 marks on that one. Okay, so question 4 then, the big question, 5 marks here. A car of mass 1,800 kilograms is travelling at 27 meters per second, that's approximately 60 miles per hour. A pedestrian steps out in front of the car a distance of 100 meters up the road. The car travels for 18 meters before the driver begins to brake. What is the average braking force required to bring the car to a stop? So there's a lot of information going on in this question, so let's get our list together. Okay, we have a mass of 1,800. We have a velocity of 27. We have a distance of 100, but then we have another distance of 18. So we'll keep an eye on that. Before the driver begins to brake, what is the average braking force required to bring the car to a stop? So we want F is what we're after here. Now the problem is we've got 2 distances, so let's have a little think here. The car travels for 18 meters before the driver begins to brake. So before the car actually starts doing any work, there's a reaction time from the driver. So we had 100 meters before we hit our pedestrian. Before we actually did anything, we travelled 18. So the distance isn't 118, it's actually 100 take away 18. And we have 82 meters to do all of our physics before this poor pedestrian meets the front of the car. Alright, so braking force, so we have force and distance. That's good, okay? So we'll probably want work done equals force multiplied by distance. The issue here is we don't have the work done. So I'm going to park this equation here. We have also mass and velocity, so we can definitely get the kinetic energy. EK equals a half mv squared. So we can work out how much kinetic energy the car has. And that's equal to 0.5 times 1,800 times 27 squared. Giving me a kinetic energy, once we grab our calculator and put in 0.5 multiplied by 1,800 multiplied by 27 squared. And remember, it's just the 27 that's squared. Giving you 656,100 joules of kinetic energy is what our car has. Right, now we're new to this concept, so let's draw ourselves a little box. So that means going into this whole situation, we have this much kinetic energy, 656,100 joules going in. At the end, we need this car to be stopped. So we need our output kinetic energy to be 0 joules. We need 0 joules of kinetic energy. Which means then that we need to waste 656,100 joules. So we need to convert 65100 joules of kinetic energy into something else. If we're converting energy from one form into another, that is work done. So the work that we have to do is equal to 656,100. And finally, we have enough to finish this equation here. We'll do it in red because we're starting to get a bit of a mucky screen. So work done equals force times distance. 656,100 equals the force which we're trying to find multiplied by the distance we have in order to stop, which was 82. Divide both sides by 82. And that's going to give us, once you grab your calculator again, an average braking force F is equal to 8001 newtons. So for every, I need to hit this thing with 8001 newtons on average in order to stop before I hit my pedestrian. Right, so mark grid for that. 5 marks available. Let's see what we've got. We get 3 marks for doing this bit. Okay, formula, working, answer. We then get a further mark for recognizing that this is the work done. That gets me my 4th mark. And my 5th mark then comes from just the answer. The intervening working out doesn't actually matter in this one. This is where the concept is here. And this is where the extra marks are available. 5 marks. Okay, I hope this has given you a slightly better understanding of kinetic energy and the types of questions that can get asked on it. Next time we'll have a look at things falling where potential energy is turned into kinetic energy, but we need to learn a little bit more about potential energy before we do that. So thank you very much for watching the video. If it was helpful at all to you, please hit the like button, consider subscribing, pressing the bell notification button, and of course telling your friends at other schools and establishments about my channel. The only payment I get is the happy and safe knowledge that my subscription numbers very slowly are going up. Okay, so thank you again for your attention, and all that remains to be said by me is don't forget everybody, physics rocks. It's true.